This recording is simple linear regression analysis. Regression analysis is a statistical technique which we use observed data to relate a variable of interest, which is called the dependent or response variable, to one or more independent or predictor variables. Object of this is to build a regression model or prediction equation that can be used to predict values of the dependent variable based on choices in the independent variables. Now we have something called a correlation. A correlation is a relationship between two variables, x and y. The data can be represented by x-y ordered pairs, like you would have learned in algebra, where x is the independent variable and y is the dependent variable. Now here, there's lots of applications for different data for independent and dependent variables. This example is I'm letting x be the number of hours studied for an exam, and we're letting y be the grade on the exam. So what you would do is you would measure different people, record their results. You'd have, okay, how many hours did you have? What was your grade? And that would get you an XY ordered pair. Now, a scatter plot is a graph that plots dots for all of these XY pairs. Now, the first one, anytime that we have a graph that goes like this, where it's going upward and the dots are clustered close together, forming a line, we call that a positive linear correlation. See how the dots kind of form almost a line? And positive linear correlation means as x goes up, y goes up. So that's kind of what you would expect for this particular model. If you would expect as the hours of studied go up, you would expect the grade on the exam to go up. Now here's an example of negative linear correlation. See how these plots all cluster together and sort of form a line? Negative meaning slope of the line is negative. It doesn't mean the values themselves necessarily are negative, although they could be. But a negative linear correlation occurs when as x increases, y would decrease. Now, if you have dots just sort of scattered all over the place, like this diagram, we would kind of say that has no correlation. Then there is another type of correlation, which we're not studying in this class, but you can have what's called nonlinear correlation, meaning the dots form some sort of curve. In this case, this is a parabola. All right, so now we have what's called the correlation coefficient, lowercase r. Correlation coefficient is a numerical measure that measures the strength of the linear relationship and the direction between the two variables. So anytime if you had the dots forming a perfect straight line with a negative slope. Now that could be any negative slope. It could be a little flatter than this, it could be a little steeper than this, but if they are in a perfect straight line, it would have a correlation coefficient of -1. On the opposite side, if they form a straight line with any kind of positive slope, we call that +1. So actually when you're measuring correlation, the strength of the relationship is actually measured toward the outside values between -1 and 1. It doesn't go increasing from -1 to 1. In fact, 0 is technically the mathematically weakest correlation that you could have. All right, so as I mentioned that right here, so this question is asking, of these two correlations, which one is the strongest? So we're not worrying about whether it's negative or positive, just which one were the dots clustered together better in a line. If you had r equals -0.8 or r equals 0.4. And it would definitely be -0.8 because it's closer to -1 versus 0.4 is farther from +1. Another way you could look at this is whichever one has the largest absolute value. That would tell you for sure too. Now let's look at what's called a simple linear regression model. Uses Greek letters. We have y equals beta 0 plus beta 1x plus epsilon, which that's an error term. anytime that you're using samples to measure a population, you're going to have an error term. The beta 0 represents the y-intercept, and the beta 1 represents the slope. So here's what I'm mentioning what the error term is. So other factors other than just x that may affect y are part of the error. So these are called the regression parameters. Now we're going to be using sample statistics, and we're going to have more of a sample model right down here, what's called the least squares line, which is our approximation of the actual parameter regression model. So the least squares line, also known as the regression line, is written as y, and that little arrow thing on top means hat. We call that y hat. So y hat equals b0 plus b1x, where b0 represents the y-intercept and b1x. This is kind of the standard way that it's written, although it's still, because it's a line, it's equivalent to the idea of y equals mx plus b. You just notice that for some reason they write it this way, where the intercept part goes first, and then the x with the slope goes second. I don't know why it's written that way. Those coefficients are known as the least squares point estimates, and the y hat is the predicted value of the dependent variable x. In other words, once you have the numbers to fill in to come up with this equation, you could then plug in any value you wanted for x within the boundaries of the original x's and predict what you think y might be. For example, for that equation of the example up there, the hours studied versus grade, I mean, you couldn't have a situation necessarily where, I study 50 hours, I'll make a grade of 142, suppose it's only 100% max. So it does have its limitations on the values you can use for x. So here's an example of a least squares line equation. Y hat equals 52.56 plus 3.42x. Now let's sort of interpret the values from this. Well, the 52.56 just is the y-intercept, meaning that's the value you predict when x equals 0. Now the slope measures rise over run, essentially change in y divided by change in x. So that means for every 1 unit increase in x, the dependent variable y will increase by 3.42 units. So in other words, if that slope is negative, then we would just say decrease. So had this said minus 3.42x, we would have said that the dependent variable y would decrease by 3.42 units for every 1 unit increase in x. So it's important when we're looking at a problem that we know the application of the problem, which one's the dependent variable x and which one's the independent variable y. So let's say, just for example, if this was the equation for the predicted score on the grade based on hours studied. So we would say that for every 1 hour studied, we are predicting a grade increase of 3.42 points. That's how we would interpret it for that equation. So this is very simple here. So in other words, predict the value of y when x equals 10. All you do is plug the value in for 10, and there you go. It would be 86.76. All right, let's look at something called mean square error and standard error. We have something called a residual. A residual is if you take the observed value for an x versus predicted value. So let's say, for example, this model up here for x equals 10. Suppose that we had a measured value that somebody studied 10 hours and made a 90, and we had a predicted value of 86.76. The residual would be 90 minus 86.76, which I believe would be 3.24. Now we have something that's called the SS error, or also known as SSE. It's the sum of squared residuals, or also known as sum of squares error. And that's basically taking each observed value minus each predicted value, squaring that and adding all of those up. And we have something called the point estimate of the population variance of this model is known as the mean square error. And the point estimate of the population standard deviation is known as the standard error. And those are just calculated. So the mean square error is known as S squared, which actually is a sample variance, but we're using the sample variance, of course, to approximate the population variance. That's just the SSE divided by n minus 2, with n minus 2 degrees of freedom. And of course, standard deviation is always the square root of variance. All right. Now, testing a hypothesis. So a simple linear regression model is not useful unless we have a relationship between y and x. In other words, to test the significance of the relationship, we have the hypothesis over here. The null hypothesis beta 1 equals 0 versus beta 1 not being 0. And you can apply this a little further. You can stretch this out and make it, you could use greater thans and less thans, but we're only dealing with equal or not equal 0. So what would happen is if we did not reject this null hypothesis, that doesn't prove the slope equals 0, but that means the model is not very significant. It's not very useful for us, because if the slope is 0, think back to graphing of lines, that would just be a horizontal line. And with a horizontal line, that means for every value of x, you would have the same value of y. So in other words, it's not a useful predictor. So ideally, for the model to be any good, you need to reject that hypothesis. So the test statistic is calculated by the B1, that slope coefficient, divided by SB1, which is this standard error S right back up here, but it's just the one measured for the B1 value. We're not going to be using anything. The only time we're going to be using the B0 is to come up with your least squares line, y hat equals B0 plus B1x. So the only calculations are involving the B1 and the SB1. So we would reject the null hypothesis if either the p-value is less than or equal to alpha, which is pretty standard, or if the absolute value of this test statistic is greater than your t alpha over 2, which I didn't write in here, with n minus 2 degrees of freedom. The n minus 2 degrees of freedom basically comes from the fact that we have two variables here, x and y. So it would be n minus 2 degrees of freedom. So if we can reject the null hypothesis, we conclude that the slope or the regression relationship itself is significant at the alpha level, meaning it's not constant. And we can also then say that the independent variable x is a useful predictor for the dependent variable y. So the value of x, y does depend on x. Now we have another measure here called the simple coefficient of determination, and that is known as r squared, which actually that is the square of that correlation coefficient we saw earlier. It's also known as the explained variation divided by the total variation. I don't think you're going to necessarily need these calculation values over here, but I wanted to include them in the model just in case somewhere down the road you might find that useful. But this is the important part of this from a wording standpoint that you need to know, is anytime it tells you it's asking for what is the proportion of total variation that is, of the dependent variable that is explained by the simple linear regression model. So proportion of total variation explained, that is the r squared value. Now you're not going to have to calculate this, but I went ahead and included I want to show you what these values were over here. We're going to get all our information from an Excel spreadsheet or perhaps some other statistical output. So I just want to show you what all these values are. We've already seen the SS error, and here's SS regression and SS total. So once again, the correlation coefficient is the square root of the coefficient of determination, but it will have the same sign as the slope of the least squares line, meaning that, because you know when you take a square root, normally it's positive, we're talking plus or minus, so if it doesn't mean it'll be the same value, but in other words, if the slope of your least squares line B1, if that's positive, that just means R is positive. They won't be the same number, but they will have the same sign. And therefore, if your least squares line slope is negative, R will be negative. So in other words, if R squared, for example, was 0.25 and you wanted to know what R was, the square root of 0.25 is 0.5. But the correlation coefficient could be either positive 0.5 or negative 0.5, depending upon what is the slope of the line. Now, here's an example where I just made up some data, going back to that model with the hours studied and grade on exam. So I just totally made these up, so I'm not going to read all these out, but you see in the left column, here are your X's, your hours studied. The Y column, I just gave it a grade based on that. I let Excel do a scatter plot to show the dots. That's forming a pretty good line with a positive slope. So that should be a pretty good correlation when it's all said and done. Before I forget, I want to mention that, before I scroll, let me come back up here. I want to mention, to kind of give you an example of something that would represent a negative correlation. Let's say if we take this, let's say if we'll keep Y as being grade on the exam, but let's say, suppose X now was hours playing a certain video game. Now, unless your exam is based on that video game, theoretically, if you're spending a lot of hours in that video game, that would mean you're studying less hours. So that's an example of one that you would expect to have a negative relationship. In other words, as X goes up, as hours played of the video game, you would be expecting the grade to go down. Okay, so I just wanted to mention that. Okay, so here's the Excel output. This multiple R is kind of the correlation coefficient. When I say a kind, I wrote over here, it just shows the positive square root, and I was mentioning earlier, but you would have to interpret this as being, if the slope is positive, then yes, R is positive. But if the slope is negative, you'd have to realize that actually the correlation coefficient would be the negative of that number. Now, in our example here, though, it is going to be positive. Now, here's your R squared. We don't worry about the adjusted R square for anything, but that's our R square. That's our percent of total variation explained by the regression model. So that's a very important number that we need to be able to find on our chart, or perhaps written somewhere near the chart. Now, these ANOVA values, that's the kind of stuff I was showing you earlier. Most likely won't be using here, but so here's your SS regression, SS residual, and SS total values. And the SS regression plus the SS residual does equal the SS total. And then the mean square is the sum of squares divided by the degrees of freedom. We won't be using that in this class, but I did want to kind of include it in the discussion. Now, this chart at the bottom is very important. So I said base, we're using alpha 0.05 here. So that's telling you intercept, and here, because I labeled it as hours studied, so the top row will be your intercept. This will be representing your X variable. So all our test statistic stuff we'll be using only from the bottom row. The only thing we'll need from the top row here is these coefficient values. So these coefficient values help you come up with your least squares line. So let's look at the least squares. So remember, the model is y hat equals b0 plus b1x. So you see right here, your b0 is your top coefficient with the intercept, 49.2.87. And then your slope is 3.326, rounded to 3 decimal places. So there's your b0, there's your b1. So your equation then would be y hat equals 49.287 plus 3.32x. Now predict the grade on the exam for the student who studied 8 hours. And plug in 8 for x, and that's a pretty easy calculation. Are the number of hours studied a useful predictor for the exam grade? In other words, that phrasing just means we want to do a quick hypothesis test, and since that output is there for us, this will be real easy to do. We want to test the regression slope equaling 0. In other words, that needs to be rejected for this to be a useful predictor, or also meaning that the model is statistically significant. Those are the same thing. In other words, both of those statements are true if you reject. So to reject, once again, I had on the other page about the p-value. So we go back up here. So there's the model right there, right? So here you go. So and I'll show you where the p-value is. We don't have to even get the test statistic t is on here. The chart value t is not on this output. The critical value t, we should say. But the p-value, so you want the p-value that's on the bottom row right here. 1.538 e to the negative 9. That is scientific notation. That's the same thing as saying 1.5386 times 10 to the negative 9. Meaning you move that decimal over 9 times, you have 8 zeros in front of it. That's a very, very, very tiny p-value, which is no doubt going to be less than alpha. That's going to be no doubt less than any alpha. You almost don't even need the alpha for this one because you're going to reject for sure. So yes, the p-value is less than alpha. We would say it is statistically significant, and the number of hours studied is a useful predictor of the exam grade. So that's not too difficult to do that hypothesis test using that output. You don't have to really calculate anything. You just have to know what you're looking for on that chart. Find the proportion of variation in the exam score explained by the number of hours studied. So once again, when you see proportion of variation of the independent variable explained by the dependent variable, that is your r-squared value, which is right above my little box right there, the 944. So as long as you know where to look for that, that is not difficult. Or that value may be written down in the problem. Somehow you have to have that number, though. All right. Now, let's look at this example that shows some missing value. Okay, here's an example that I was using the hours playing a video game as an example of negative relationship, but here's a good one. Class absences. Now, this might not be true in all cases, but on average, you would expect someone that misses a lot of classes to do worse, but you have the occasional student that will still do okay, that can study independently. So maybe perhaps I should have put a value on here where it kind of spiked one off up high here for the, that they, even though they missed a lot, they still did well. But this is pretty reasonable what you might expect. So class absences is your X, and then we're trying to see if the grade on the exam is dependent upon class absences. Now, I left the multiple R to R out here, the correlation coefficient. I did that on purpose. And I also left out the test statistic on purpose. So if you come back up here, let me show you this. We didn't need to do it for this last problem, but let me show you that when we come down to this next one. Look how you calculate that test statistic. This first value on the bottom row is your B1 we've already used. The standard error is the standard deviation, SB1. That's right next to it on the bottom row. And that T-stat literally is calculated as B1 divided by SB1. So as long as you know those first two numbers, the coefficients and the standard error, you can get that test statistic real easily. Let's go back to our model. And first thing I said is let's write the least squares equation. So notice here are your values, your coefficient values. The y-intercept, the B0, is 96.935. Your coefficient for your slope is on the bottom row, negative 0.4939. And you see the graph shows you it's a negative slope. And so let's say we predict the grade for a student who misses 2 classes. So we plug 2 in there and we get 87.057. Now are the number of class absences a useful predictor for the exam grade. So just like the last one, let's look at our p-value in that bottom row. And there it is, 4.14 times 10 to the negative 9. So yes, that's very, very small again, so we would absolutely reject. So it is a useful predictor, and the model is statistically significant. Both. Proportion of variation explained by the number of class absences. That's our R-squared model, right? R-squared value. We never use the adjusted R-squared. So it's the 0.935. Of course, that could also be written as a percent, so it might say 93.5% because it may say percent of variation explained. No problem to convert that. Determine the correlation coefficient. Now, this is where I wanted you to use the idea of, so that's R squared. So what we'll do is to get the multiple R, it's going to be either the positive or negative square root of 0.935. You'll see the calculation here in a minute. It's the square root of that number. It's going to be either plus or minus. As I mentioned earlier in the notes, that the sign of the multiple R will match the sign of the slope coefficient down here in this bottom row. So this time our slope coefficient is negative, so that way our correlation coefficient will be negative. So that's what dictates the value, and as I wrote right here, it is negative since B1 is negative. So it's the negative square root of 0.935, which will be negative 0.967. And calculate that missing test statistic. So I've already told you how to do that, but for this example, real easy. You'll just take the first number in the bottom row, the coefficients of negative 0.4939, and divide it by the 0.36. And that'll tell you the test statistic number that I took out of there. So there it is, negative 0.4939 divided by 0.36 is negative 13.719. And the last thing I want to show you here is, it looks like the first two models I did were very strong models, meaning we rejected them and correlation coefficients were high. I mean, they were very, very good. So you kind of don't want to fall in the trap of thinking, well, every time we do this, we're automatically going to reject. You can have some bad models come up. Now look at this one. I didn't really give a story to this one as far as what the data is representing. I didn't even label anything here, but you would assume the first column is the X and the second one's Y. But look at some of these values. 5 goes with 15, 3 goes with negative 11. Look at some of these. 8 jumps to 50, 4 goes to negative 10. It's all over the place. So I put it in Excel and did the output just like you'll do on the assignment for Stat 3309. Okay, so the only thing I want to point out here is just the rejection of whether we reject the model or not. I didn't ask a lot of questions on this. Look at the p-value for the x variable. So if that x variable didn't have a name, like this one didn't have a name, so it just shows x variable. Look at that p-value, 0.25. That's a pretty high p-value. So this p-value 0.25, it did not matter what alpha I put, whether if you use 0.01, 0.05, 0.10, 0.25 is greater than all of those. Therefore, you would fail to reject. So we would say this model is not a useful predictor. X is not a useful predictor for Y. And it's not statistically significant. And you look at the data, and it kind of shows you it's all over the place. Correlation coefficient's not that great. It's no good. So they're not always going to be reject. So I wanted to point out one example. And I believe that concludes the lecture on simple linear regression analysis.